link? Okay. I had some students ask me for recording, so I'll just do that right now. Okay, didn't miss much. So moving on, if x is 0 in this case, I'm going to have 0 minus 1, which is going to be minus 1. So it's still negative here. And it is actually negative all the way to 1, where it becomes 0. And then it becomes positive again. Okay. Now we have x minus 2. Again, if it's negative, 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 it actually happens at 0, at 2, that I have a 0. And then I just have positive, positive, positive again. Okay? So the thing the drawing is relatively simple. So now I can maybe just get some idea on what the sign for f of x is. Okay? So if I look up top in my case, between minus infinity and 0, I'm going to have minus times minus times minus, which is going to give me minus. Okay? I'm going to have 0 here. And then what's going to happen between 0 and 1? I'm going to have plus, minus, minus. So this is plus, plus. Okay? Another 0 here. Then between 1 and 2, I'm going to have plus, plus, minus. So this is minus, minus until 0 here again. And then I'm going to have plus, plus again towards the end. Everything make sense? Everyone follow me on that? It's just this graph, this table, whatever you want to call it. It's just me basically taking values of x and seeing where these change sign. If you don't like this table, another simple way to do it is to just say, okay, I have these 3 elements, 1, 2, 3. So I'm just going to look at, if x is greater than 0, only if x is greater than 0, I don't know what to say, then x minus 1 is greater than 0 if x is greater than 1. And then x minus 2 is greater than 0 if x minus 2. And then you basically just take all the possible cases, such as case 1, x is greater than 2. And then you're going to have, so again, if you're happy and satisfied with the table, then you don't need to look at this. This is like another way of doing stuff. Okay? It's just basically breaking the whole space into cases. I'm looking at f greater than 2, f of, with x greater than 2, and I'm going to have x minus 1, x minus 2. I'm going to have positive, positive, positive. So this is a good case. Then I'm going to have case 2, where I'm going to have x is smaller than 2, but x is greater than 1. And in this case, I'm going to have f of x is equal to x minus 1, x minus 2. So because x is smaller than 2, I can say that this is going to be negative. X is greater than 1, this is going to be positive. And this is again going to be positive. So I only have one, I have positive, positive, negative. So this is smaller than 0. So this is a bad case for me. Then my case 3 would be x is smaller than 1, but x is greater than 0. And then my f of x, we look at it again. And I get this is greater than 0, this is smaller than 0, this is smaller than 0. So I have positive, negative, negative. That gives me positive. So this is, again, good. And my last case is case 4, which I have x is just smaller than 0. In this case, surprise, surprise, I'm expecting all my elements to be negative. So this is negative, this is negative, this is negative. So my end result is going to be negative, which is a bad case. Okay. This way of solving stuff with cases is basically just writing out loud with a little bit more detail the whole table thing. Regardless, the answer is the same, and that is f of x is positive if x greater than 2 or x is greater than 1, no, it's smaller than 1, greater than 0. Well, in these cases, it's going to be fine. Cool. Now, for the next part, we're asked to basically take a derivative, analyze it, see where it's increasing, decreasing, basically everything you can do with it. So let's just do it. Then it asks us about convexity, etc. So let's do that as well. So B, I have f of x is equal to x minus 1, x minus 2. Okay, we have to compute f derivative of x. Now, you can either use the chain rule or the product rule, I mean here, and just apply it several times, or if you're just more into, I guess, if you're fast at simple computation, I think I'm fast at simple computation. I'm just going to open the parentheses, and then I'm going to take a derivative of everything because I'm going to have a polynomial, which for me, it's much easier, and I know I'm not going to mess it up. So what I'm saying, again, is that you can take a derivative and say, okay, this is my first term, this is my second term, and then write it as, oops, sorry about that. Write it as x prime times x minus 1, x minus 2, plus x times x minus 1, x minus 2, everything derivative. And basically then apply another product rule. So this is just the product rule, and you can do it like this. It's perfectly fine. Maybe I work differently. The way I would do this is I would just write this in. I would just open the parentheses and I'll get x, open the parentheses there, and I get x squared minus 2x minus x plus 2, which is going to give me f of x is equal to x to the third minus 3x squared plus 2x. Okay, and I'm going to take a derivative of this. I don't know, it just works for me. Any questions on this? Okay, cool. So my derivative then is just going to be 3x squared minus 6x plus 2. Okay, so this is the derivative. And as far as I remember, just quick alt tabbing here, it asks us where it increases, decreases. Okay. So let's first assess where is f increasing or decreasing. And perfect. Okay. This is what I'm going to look at first. And what do you know? You know that really important that this is something that you should try to make it big again. Okay. Something you should remember or know because it's really useful. The idea is that if f prime is greater than 0, then you have that f is increasing. And if f prime is smaller than 0, then you have f is decreasing. All right, this is something that you should know. You should know by now. Okay. So let's so I'm gonna need to try to see where this is greater than 0 or smaller than 0. The f prime. The problem is that I'm dealing with some kind of squared here, and they're usually a little bit ugly to give the signs right off the bat. So whenever you're asked to look at the sign of a square, the easiest method is to just compute the roots. Okay, so let's just compute the roots of this. So for now, to answer this question, for now the answer is I don't know. Okay? Question mark. For now, I can't tell. But I'm gonna do the critical points and solve the equation. So for critical points, remember f prime of x, it has to be equal to 0. So I just have 3x squared. If I can mess it up. Yep. 3x squared minus 6x plus 2 has to be equal to 0. Okay? So the simple way to do this is just use the delta. And we're gonna have 36 minus 2 times 3 times 4. That's about right. Okay, so this is gonna give me, this is 24, so it's gonna give me delta is equal to 12. Okay, so my x1, x2 roots are minus b, so plus 6, plus minus square root of delta over 2a, which is 2 times 3. Everyone follow me on that? Makes sense what I'm doing?
What is that? What's that thing?
This one?
Yes.
It's just, I don't know, isn't this how you learned it with the delta? It's just a notation.
Yeah.
It's just the delta is b squared minus 4ac. I thought it's an international notation, but I might be wrong. Okay. ABC rule. ABC rule. Okay. Sorry. Okay. Now, does everyone follow me on what I did with the ABC rule? Cool. Okay, so I found my roots. Now, you can either remember this by heart, or you can just draw it. It makes sense both ways. So, okay, regardless, I found my critical points. These are my critical points. I solved the second part. I still have not solved. Okay, let's put 12 here, so I don't have to write ABC rule again. Okay. So I got this answer. You can simplify them, yes. Do I really care to simplify them? Not really. You're not gonna ever lose points on the exam if you just leave it like this as opposed to simplifying it by 2 or 3. If anything, and you find someone in a bad mood, you might lose 1 out of 10 points. I guess for me, I'm too lazy to do that. So you get these points, and now we still have not answered the question: where is f prime of x positive, and where it is negative? We need this to see where the function is increasing. So there are 2 ways. The first is if you have, like, I'm gonna write it as a theorem kind of thing. I don't know. But the idea is that if you have something like ax squared minus plus bx plus c, which is the quadratic, the normal quadratic, which is our case. Let's say this is equal to my f of, let's use g of x. Okay, if this is my function g of x, then g of x is going to be, it's, okay, yes, okay, let me erase that. The way the theorem goes is that if a is positive, so the dominant coefficient is positive, then you have that g of x is negative between the roots. And g of x is positive outside the roots. So if you like this, if you know this, fine. If you don't worry, I'm gonna make a drawing that's gonna make everything simple, and you're gonna understand why I'm saying this. So our function 3x, our initial function f of x, which is 3x squared minus 6x plus 2, looks something like this. Okay, because this is positive, because the coefficient here is positive, the graph is always gonna look like this. If you don't believe me, just graph the numbers, but I think this is more or less common knowledge. So since it looks like this, the whole idea is that these points are your roots. Like these points would be, in my case, plus 6 minus square root of 12 over 6, and 6 plus square root of 12 over 6. Okay, these are the roots, the points in which my graph, my f, this is f prime, my f prime of x intersects the x-axis is where I'm gonna have the zeros. So these are the roots. And now if you look at the graph, where is it negative? Well, it's negative here, right? It's below the x-axis, so it's negative. So here it's gonna be negative because below x-axis. And here, I don't have colors on this, so but here it's going to be positive above the x-axis. Did this make sense? Okay, so in order to kind of answer the question that the problem put on me, which is where is f prime x positive? It's got to be positive in the interval minus infinity plus 6 minus square root of 12 over 6 and 6 plus square root of 12 over 6 infinity. This is where it's going to be greater than 0, at which point means that f of x is going to be increasing according to the observation that I made initially. Right here. Okay. Right here. So coming back, I have that the function f of x is going to be increasing in this interval. And then where f prime of x is smaller than 0, which is in the interval plus 6 minus square root of 12 over 6, 6 plus square root of 12 over 6. This is where it's going to be negative. And so if the derivative is negative, it means my f of x is going to be decreasing. Sorry for that. It's going to be decreasing. Anyone got questions on anything that I did up to here? Literally anything? Okay. Cool. So yeah, I think the last part of the problem they're asking us is where is f of x truly convex, which is asking us to take another derivative. When we're asked about convexity, you're asked to take a derivative. So f double prime of x, I'm gonna can I put it in the same screen? Not really. But I hope you have it written down. It's just going to be 6x minus 6 if my derivatives aren't bad. And now it's asking us where is it strictly convex? Greater than 0. So it's going to be strictly convex if x is greater than 1. Then f strictly convex. Cool. Everyone on board with this? Good. Then this was the first problem. Okay. So yeah, we're just gonna move on. Let's see, not the compendium. Also, right now I can give you, I'll give you these notes. This is the reason I'm writing on this thing so I can post them faster. Oh no, okay, we have to do problem number 2, which is the compendium 43, which is the ugly derivative that I hope we're actually gonna avoid, but I guess we're not. Yeah. Okay, problem number 43. Okay, now I remember it. So the ugly problem, problem number 2, which is like 43 from the compendium. And it was, they gave you this function, which I need to see again. X defined by n g p of n over n. And now they just make a compute there. Not touching it. Okay, cool. So we got to compute just this derivative, right? Simple. Or is it? Yeah. Whenever you're stuck and have to compute difficult or complicated or ugly looking derivatives, or all of the above, actually, you just got to start simple. Like that's my trick. Start simple, and then keep on going simple until you're done with the problem. Like for example, I'm pretty sure maybe, I don't know, maybe some of you could just give me this derivative like in one line, but I don't know if I could. Anyway, so my idea here is I have no idea how this function is going to look like, but what I do know is that I can split this ugly looking formula into 2 parts. This is my first, and this is my second. Okay, why do I do this? Because if you look more closely, you can see that it's just a product. Okay, so I'm just going to apply the product rule to it. So what's the product rule? It's n g p of n over n plus n g p of n over n. Okay, and the way you do it, I think you just say derivative this and then derivative of this. Okay, everyone agree with what I did? Just a product rule, nothing special. Now let's see what I got. N derivative is just 1, so I'm not even gonna write it already. Plus n times g f of n over n. Okay. So am I actually looking better? Well, kind of. This part of the function, this is done. Okay. There's nothing for me to do here. The only thing I have left to compute is this ugly thing. So I have left to compute. So let's just, instead of like writing the whole equation 20 bazillion times, what if I just compute it separately right here? Okay. And I've seen you guys work with, let's just say this is a u of f. So let's just do that. This is g of u of n, everything prime. So this is just going to be what, according to, I think, the chain rule? This is just going to be g prime of u of n times u prime of n. Also, one thing that I want to get your attention on is where I put my derivative. Okay. When I'm, for example, here, when I'm taking a derivative of g of the function, my derivative is of everything, okay? While opposed to here, where it's g prime of u of n, okay? So be really careful where you put the derivative. Like, for example, here I'm taking the derivative of everything, and here it's the g prime of u of n. So really, really careful where you put those signs, because it might end up costing you. Okay, but let's just replace. So equal again, and I get g prime of phi of n over n times phi of n over n prime. Okay, okay, this is done. So all I have left to compute is this fraction over here, left. Now I'm just gonna apply the quotient rule to that. So let's just move on to the next page. So I get phi of n over n prime. What is this equal to? I just said I'm gonna apply the quotient rule, which goes something like f over g, everything prime, is f prime times g minus g primes times f over g squared. Is this actually? Yeah, I think it is. Looks like it, right? Okay. Cool. So I'm just going to apply this formula right here, the quotient rule. And I'm going to get phi prime of n times n minus n prime times phi of n over n squared. Now, if you guys are faster than I am with computation, or this is too slow or whatever in the exam, nobody's asking you to do all these intermediate steps. I'm just doing it to show you guys my way of thinking, I guess. But, you know, if you're whizzes or whatever, you can just do it in your head and write the answer. I don't really care. The only drawback of just writing me down the answer is if you mess up in your head, I have no idea of telling whether you know what you're doing or not. Well, if you show me the work like here, and I see the mistake, I can more or less backtrack through your problem and see where you made the mistake. Like, for example, say I just had a plus here by mistake, okay? Let's just say it happened. If you show me all the work like this, then I can say, oh, he just messed up a small formula here. As opposed to just spitting me the answer with the plus, I'm gonna be like, yeah, I have no idea what this guy's doing. Maybe he has no idea what he's doing. Okay, so that's the trade-off. Take it as you want, do as you want. I'm just giving you the pros and cons of everything. Anyway, so this is the minus, and this is just going to be phi prime of n times n minus phi of n over n. Okay, and I'm done. Now I just got to write everything nice. So I'm on different pages, but you guys, could see on your notebook, dx dn is going to be, let's copy from the back. This g of phi of n over n plus, what do I have? I have an n times this thing over here plus this thing over here. I mean, multiplied by this thing over here. G prime of phi of n over n times this derivative, which I just computed right here. So there's an n squared, by the way. G prime of n. Okay, let's not write it there. Times phi prime of n times n minus phi of n over n squared. And I'm done. Okay. Was that more or less easy to follow? Then, then let's do the second derivative, which I know everyone is excited to do. Okay. whenever you're asked to do I usually tell you that there's no reason to simplify or whatever, which I kind of support because I've always been the laziest student in the world. But in this case, since I have to take a second derivative, I'm just gonna look for 1 second, like, realistically 1 minute, and see if I can simplify something. Because any simplification that I do right now is gonna help me a lot when I'm taking the second derivative, especially if I'm breaking it up like I did right here. So I stare at it for a second, and the only simplification I could find is this n squared simplify with this n over here. That's the only thing I could find, unfortunately for me. So yeah, let's just do the second derivative right now, and then we're gonna do like a 5-minute break because I was late. Sorry for that. And then we're gonna keep on going. Okay, does that work? Cool. So do you guys really need to see the second derivative? I don't think it's necessary. Okay. Cool. So first of all, I have to take a derivative of this, which, if you look through your notes, we already did. Okay. We already did take a derivative of that. It's right here. Okay. So there's no need for me to recompute it. I can just spit it out. It's this. Derivative of this is just g prime d of n over n times this ugly thing. Okay, just to be clear, this is this thing. And the reason I wrote it right out all of a sudden is because we already computed it. Okay, I'm actually gonna write already computed it on our page. So nobody's gonna give me a medal for computing the same thing twice. Okay, plus, and now it's the ugly part, because I have to compute the derivative, g prime d of n over n times p prime of n minus p of n over n, everything prime. Okay, so again, I don't know how this is gonna look, so I'm just starting simple. Again, first term, second term. And what am I gonna do again? You guessed it, I'm just gonna apply the product. And again, I'm not gonna carry this thing after me until the end, just because it's an ugly formula and there's nothing I can do with it right now anyway. So let's just work with this for now. So according to the product rule, that's just gonna give me g prime p of n over n times p prime of n p prime of n times n, I think it is, minus p of n over n plus g prime p of n times okay. Here I have to take a derivative of this whole thing, and here I have to take a derivative of this. Okay. So let's do the first one. Let's do this one. Let's call this A. Let's say this whole thing is A, and let's say this whole thing is B. So A is going to be equal to, what's this derivative? Well, again, I have to compute g prime of u of n. Okay. Everything derivative times p prime of n times n minus p of n over n. Okay. Doesn't this look really familiar? If there was no prime here, it's the same problem we had before, right? So what's actually going to change? I'm just gonna have double prime on G. So this is just gonna give me G double prime of U of N times U prime of N times this everything. Okay, everyone okay with this? Okay, we're gonna assume the answer is yes. Okay, now this U prime, I already computed 20 times already. It's right here. So I'm just gonna copy it. And I'm going to get G double prime of U of N times P prime of N times N minus P of N over N squared. For completeness reasons, I can drop the U of N. I can just write the actual fraction. Okay. Everyone agree with this? Okay, now I'm done with this. Can I do some simplification with it? Kind of, I guess. What simplification can I do here? It's not necessarily simplification, just a more compact way of writing. This is the same as this. Right, so I can just write this as G double prime times 1N times phi prime of N times N minus phi of N over N, everything squared. Okay, it's just a more compact way of writing. Okay. Yeah, now let's compute B now. We're gonna do it on the other page. B on the other page. So remember, my B was G prime of phi of N. And again, the position of the prime actually counts a lot, because if it's G prime here, it means I'm done. There's not much I can do to it. If hypothetically it was outside, it meant I still have to compute the derivative. But since it's there, it means I'm done. There's nothing I need to do to it. Okay? Times phi prime of N times N minus phi of N over N, everything prime. Okay. Might look ugly, but what I'm going to do here is I'm just going to apply the quotient theorem again, the quotient rule. I don't know exactly how you call it. But this is going to be equal to phi prime of N times N minus phi of N, everything derivative. Let's actually write it down so I have more space actually. Let's write it down here because I want more space. So I'm going to have a huge line over here, and I'm going to have phi prime of N times N minus phi of N, everything prime times N minus N prime multiplied by the parentheses with no prime over N squared. Okay, this is just the quotient rule applied to the whole big thing. So now, what do I get? I get G prime phi of N over N times, and let's do another big bracket over here, N squared. And these ones, like, I think I'm confident to do them like in my head or more or less. So this is the product rule. So I'm going to get the double prime of N times N plus phi prime of N minus phi prime of N
times n minus phi prime of n times n plus phi of n.
Okay. I see that this goes away, which is great. And some other things that can happen is I get G prime. Again, more compact writing. I'm not doing much. I'm just writing it, I guess, a little bit nicer. And I get P prime of n, because I had an n here and n here, n squared, so it goes away. Minus P prime of n plus phi of n over n squared. This doesn't look that bad, right? Kind of. Anyway, let's just group it all back together now. So I have my A, I have my B, I have literally everything. So it's actually harder for me because I have like smaller pages than you guys. But you know, you can use in an exam if you have to compute something like this or etc. You can just use what's it called? You can just use your scrap paper, and it's gonna be fine. Okay, so we're here. This is where we started. So let's just replace everything. So I got, oh, that's a lot to replace actually. So I have my second derivative of x with respect to n, and I'm going to have g prime of phi of n over n times the phi prime of n times n minus phi of n over n squared. That is my first term. Now, my second term, let's look again. This is actually a little bit of stuff. Okay, my second term is going to be this whole big thing, which if I go on the other page, I split into A and B. Okay, my A is this, so I'm going to put this in, and I get plus G double prime phi of n over n, and here I have what was it? It was phi double prime of n. Okay, I don't know. Let's see again what it was. Phi double. It was G double prime of phi n times 1 over n times that thing. So it had nothing to do with what I was saying. One over n times phi n minus phi of n, everything over n, everything squared. Okay, this was my second term. And now my third term was plus. Third term is hopefully on the other page. It's this one. So I'm just gonna take this one. G prime of phi of n over n. And I have phi double prime of n minus, let's see how I wrote it. Well, I wrote it right here because I want to keep. Okay. Actually, one mistake here that nobody noticed. So I opened the parentheses right here. I opened the parentheses, so I have minus, stays minus, and then minus with minus comes plus. But when I write it like this, which is, I guess, a bad writing in this case, this thing becomes minus again. That was one thing that I didn't take into account, but I took it down. Minus phi prime of n times n minus phi of n over n squared. Okay, so this is my final answer. Now, you might say, this doesn't really look like the one in the book. Yeah, the reason why this doesn't look like the one in the book is because I can do one additional simplification. Look at this element right here. I have g prime times this whatever thing, this whole fraction, which is the same as g prime and this fraction over here. So what I can do is I just simplify it. This goes away with this. And now you should get the result in the book. Okay, we'll end on that. We're gonna give like a 5-minute break and then we're gonna keep on going. If you have any questions, just call in and ask.
Okay.
I think you missed it. But it's fine. That's doesn't matter. Oh guys, I guess most of you are back. So we're just gonna keep going with problem number 3. If there are no questions here, let's go problem number 3. Okay. I am partially mad because I think he should have given problem number 3 in the plenary session before last week's exercises. Because remember, I think last week on the ugly problem, I kept saying that, hey, if you would have done the problems in group 1, it would have made so much more sense. So here we are doing things the other way around, but it is what it is. So problem number 3 asks you if there's a maximum. So is there a global max for the following functions? The first one was f of x is equal to 1 over x minus 1, I think, with x greater than 1. Just double checking fast. Yep, that was it. Yep. Okay, so okay, 2 ways of doing this, actually multiple ways of doing this. I'm just gonna take the, I guess, more intuitive option. Can you take a derivative? Yes. Okay. First misconception I actually want to address is, you know, the extreme value theorem. Extreme value theorem, which in the simplest words possible means that if your domain is like this, it has a maximum. Okay? This is like the simplest way of me writing the extreme value theorem. Now, a common misconception that I've seen across a lot of people is that if it looks like this, then it does not have a maximum. And this is false. Okay. Just because it looks like that, which means that it's open, it can be like this. Okay, no zero here. Because it's open, it just means you can't apply the extreme value theorem. But it does not mean that it doesn't have a maximum. Okay? So if it's like this, it means that you can't apply the extreme value theorem, but it doesn't mean it doesn't have a max. Okay, so this is something that I've seen across. Why is it so funny? Much better. Okay, so this is actually something that I've seen across a lot of people. If it's closed, then yes, you can apply if it's closed, if it looks like this, then yes, you can apply the extreme value theorem and you're done in one line with the whole problem. You don't care anymore. But if it looks like this, or it's open on both sides, it just means that you cannot apply the extreme value theorem. It does not mean that just because you can't apply it, it doesn't have a maximum. Okay, are we clear on this? Because this is like a big, big mistake. Okay, so in this case, my interval, since x is greater than 1, my interval looks like 1 open infinity. Okay, so I can't apply the extreme value theorem. Again, it doesn't mean it doesn't have a global max. It just means I have to work a little bit harder. So I have f of x is equal to 1 over x minus 1. And yes, you can take a derivative. Yes, you can make it however you want to. But what I would suggest is sometimes you have like some nice looking function. Just spend 1 minute. You have 1 minute to spare in the exam. And just think about it. What does it mean to have a maximum? Okay. What does it mean to have a max? Okay. It just means that I can find an f of m that is equal to some value m, such that any x greater than 1, f of x is going to be smaller or equal to m. Do you guys agree that this is the definition of the global maximum? It just means that if it has a global maximum, it means that there is a biggest value. Okay? Cool? So let's look at it. Is this actually tuned for this function? Well, what happens if I just put in x is equal to 1.000001? Okay? Well, let's just see. F of, I'm not going to write all these zeros again. 0, 1 is going to be 1 minus 1 is going to be 1 over 0, 1. Okay? And what's the idea? Why did I write this many zeros? I'm just trying to show you that I can make this f of whatever equal to 1 followed by how many zeros you want. 1 trillion, 1 trillion of a trillion. I don't know. So then I'm asking you, just conceptually, is there such a thing? Is there like such a number such that all the values that come up with are smaller than that? Like, can you give me a number such that all f of x's are smaller than that, smaller or equal to that number? Well, the answer is no, because whatever number you give me, I can create one bigger than that. Right? Make sense? Like, this is just, I guess, the simplest way and the fastest I would use it. I don't know. If you don't like this one, what I can do is, I guess, you can take a derivative. But for me, it wouldn't be necessary. Again, just to repeat the argument for the sake of the argument, I just asked myself, what does it mean to have a max, a global maximum? And the definition is that I can find a number so big that it's bigger than all the values that the function can take. Okay? It just means that whatever number I put in here for x, it's going to be smaller than that number. And that number can be whatever, 1,000,005. I don't know. And then I gave you the example that I can just create this number, 1,0,0,0,1, or 1, how many zeros you want? 1, which if I plug in f, it's going to give me any value of f I want. Okay? So my idea is assume it has a max. Okay, and that's f of x is smaller than OM. This is what it means to have a max. And then I just take an f of 1,0,0,0,1 that is going to be greater than f. So I'm going to get a false, a contradiction. So it's given that I can find in the function bigger and bigger numbers without limits, I'm going to say it doesn't have a max. That's kind of the idea. Now, if you don't like this argument, I have another one for you, which maybe is closer to you, although I would, I'll just spend some, like, I don't know, 5 minutes, I guess, to try to understand this, because I personally have not seen this in math too, really, this kind of argument, but the professor has given this type of argument 4 times already across everything. So he kind of really seems to like this argument. Does that mean it's going to be on an exam or something? I have no idea. I'm just giving you my 2 cents. Okay. The other argument that you can use here is the following: is you take a derivative and you're going to get, we're going to write it straight out. It should be this. Okay. What did I tell you on the first plenary session about squares? Most important thing, they are always greater or equal to 0. So if they're always greater or equal to 0, it means that this function is smaller or equal to 0. I guess strictly small in this case because this can't be 0. But let's use strict for the sake of conversation. Okay. Building up, I told you that if the first derivative is negative, means the function is decreasing. Okay. So given that the function is strictly decreasing, and I'm working with the interval 1 infinity, it just means that my graph is looking something like this. So this is 1 over here. And let's just say, just keeps on going like that. And goes like that. Okay. Cool. So, and it doesn't intersect, it just keeps on going up. I just don't have where to draw it. So in this case, does it have a maximum? No, because the function is gonna, around 1, it's always gonna keep growing, okay? Because it's decreasing. It's decreasing. So I can always find a bigger number to the left. Yeah, this is the other argument that you want, that you can use. Any questions on any of the arguments? Okay. Let's move on to the next one. Point B, I'm going to write it right here because it's the same function. Point B is f of x is equal to 1, x minus 1. This time, x greater or equal to 2. So my domain of definition is x into infinity. Okay, it's the same function. So it means that f is still decreasing. This time, because it's closed on this side, I'm saying that it has a maximum. And I'm actually telling you that the maximum of this, the global maximum, is f of 2. Okay. Think for a second. Because it's decreasing, okay, so there are 3 arguments that are carrying me here. 1, 2, I mean, that's kind of it. This is just the answer. So 2 arguments that are carrying me. The fact that it's close to the left side, and the fact that it's decreasing. Then my claim is that f of 2 is maximum, is the global maximum. Let's think for a second. Why is it? I'll show you. We'll give it literally 1 minute for those of you that haven't been in the session. Think of the definition of maximum. Write a definition of maximum and then tell me why is it true. Okay. Actually, I'm gonna do it actually. Okay, so I said that f of 2 is max.
This means that any x you get me in the interval to infinity, f of 2 is greater or equal to f of x.
Okay, this is what it means to be the maximum. Again, I'm not doing anything fancy. I'm just writing the definition of the maximum. Now, why is this true?
F, remember, f is decreasing. So I have f of a is greater or equal to f of b. Then I have a smaller or equal to b.
So what is the argument? The argument that
This is true is because 2 is smaller or equal to any x into
infinity, right? Like if it's decreasing, if my function looks like this, I'm gonna draw it again, kind of. So we established that my function looks like this. Disclaimer, I don't really know if this is how it looks, but I'm assuming this is how it should look. Okay. If this is how my function looks, it's decreasing, it always goes down. And I just put this 2 over here. Where's the maximum value? The maximum value is going to be at this 2, right? Because if I go to the right, it just gets smaller and smaller. So the maximum is going to happen here. Okay. If the function is decreasing, the maximum is always going to be to the left of the interval, and the minimum is going to be to the right of the interval. Okay, makes somewhat sense. Like I showed to you guys that it's decreasing. This is the definition of being decreasing. It means that the smaller the x, the greater f of x is. So in words, it means the smaller x is, the bigger f of x is. So if I want the biggest f of x, I'm just gonna take the smallest x, right? Doesn't it make sense? I'm just gonna, if this is true, then for the biggest f of x, I am going to take the smallest x. And now I'm asking, what is the smallest x into? What is the smallest number into infinity? It's just 2. It's 2. So this is my answer. It has. And it's actually f of 2. Made sense? Somewhat? Follow it? Okay. Now let's get to point C, which is by far a little bit more confusing, I think. So f of x is this. And no, I would not recommend you take a derivative of this. I don't even know if it's going to be helpful. Anyway, it's defined for all x. Okay, and he gives you the hint, which is really helpful. He says that if x is very big, oh sure, I mean it's here, but I'm just going to show it. Yeah, I just wanted to plug in the numbers. Okay, if x is very big, then he says that f of x is approximately 0. And then he says that if x is very negative, then again, f of x
is approximately 0.
That's what he says in the here, in the hint here. And then he gives you an example that if you have f of 5, he says that, you know, f of 5 is like smaller than 0, 0, 0, a lot of zeros, 5 something, okay? So he's basically saying that your function there's no sign. He's basically saying that your function after some numbers here and here is very small. It's like this. Okay, that's exactly what he's saying. If x is very big, then it's approximately 0, so it's approximately 0 here. And if x is very negative, it's approximately 0. That's what he's claiming in the hint. Now, can you answer, does this function have a maximum? If on the outside of this is very, very small. So here it's approximately 0. And now this is kind of the argument. We said from the start that my interval defined for all x is minus infinity. There is no way I'm applying extreme value theorem to this. Okay, so it means no extreme value theorem. But what if my interval was of the type minus? I think he uses a, where a is some big number. What if my interval looks like this? Can I apply extreme value theorem to this? Yes, that's the idea, that I can apply extreme value theorem to this. This, I can apply extreme value theorem. This has a maximum. Okay, so the whole idea here is that if I just create my interval, this is my a, this is like my minus a. The whole idea on this problem is that if I create this interval, okay, minus a and a, I know that inside here, I have no idea how the function looks like, but I know there is a max. Everyone agree with my claim that in this interval, a, for any number a in the world, I have a maximum inside this, just from the extreme value theorem. Now the question is this maximum a global maximum? And the answer is yes. Why is it a global maximum? Because everything outside of this interval is extremely, extremely small. It does not count. Like my maximum here can be, I don't know, you can give me a very big number, a very small number. It can be 0.2. It doesn't matter. The idea is that outside of this, the numbers are 0, are close to 0. You saw how many zeros there are in his hint for an A5. Imagine how many zeros you're gonna get for an A100. Okay? So kind of, did you guys follow kind of on this argument? So my argument was minus infinity, no way I can apply extreme value theorem to this. So on the other hand, if I have this interval minus a, I can apply extreme value theorem to it. And I know there's going to be a maximum inside this interval. Now the question is the maximum inside this interval the global maximum? Okay? And then the hint comes into play, that if x is very big, that if f of x is very big, then the function is approximately 0. And same for negative. So then, knowing that on the outsides of the interval, it's 0, like here it's 0, here it's 0, the maximum that I'm going to find in this interval is definitely bigger than anything I'm going to find on the sides. Okay? So that idea is the maximum that I'm finding in this interval is actually the global maximum. That's kind of the idea that's driving this whole thing. So the way I would write it is, okay, minus A EBT has a maximum, okay? Which is going to be the global maximum. By the way, this is my short form. I don't think it's international by any means. It's going to be the global maximum because it's zero, because the function is zero, whatever. Because the function is zero outside the interval. Okay, this is kind of the argument I would write, and I would be perfectly fine. Yeah. No, the log, you can only. So first of all, you can take log of only positive numbers, but the log of numbers can be negative. Like if I give you log of 0.5, that is a negative number. Secondly, you're asking me if it goes on like this. Like this? No, that's fair. And I guess the argument that I would use for this is I would just take f of 1, which is 1 over e, and this is a positive number. And this number, because it's 0 on the outside, it's gonna be bigger than anything on the outside. So I already have a bigger number inside the interval that is bigger than anything on the side. So I don't really care how it looks. I think realistically, if you want me to graph mentally how I think this graph looks, I think it looks something like drops like this and gives something like this. I have no idea, and I personally don't care. That's the beauty of the extreme value theorem, that you don't care what's happening. As long as you have some like claims to help you, you don't care how the function looks like. You just know it has a maximum and you're done. Okay. Now, a little bit short on time. So, yeah, very short on time. So what we're gonna do is the following. You had this problem 4, which I think is, yeah, I'm not gonna express my opinion because it's not a good one of this problem. So I'm not gonna dive into it. I don't think it tests much that you would need. I'm gonna do problem 5 because it's exactly one line. Actually, I do have 2 minutes to spare. So if you have not done problem 5, just spend 2 minutes on it. And I'm gonna, like, how would you solve problem number 5? It's 2 minutes is maybe too much. It's 1 minute, it's one line that involves no computation. How would you solve it? Problem number 5, problem number 6, I mean. It's a typo here. The last problem should take you 1 minute flat, maybe less than that. So I'm gonna give you 1 minute to think about that, and then we're gonna solve this one from the compendium, and the remaining 15 minutes. So just think about it. On the last problem, hint, you do not have to compute the derivative of that thing because it's gonna be really, really ugly. It's one line, no computation, just, yeah. Meanwhile, I'm gonna try to think about how to solve problems. No. Okay, have you guys figured it out? How to do it? As I said, I'm not lying.
That's problem number 6. It's one line. Explain why the function f of x, blah, blah, blah. F of x, blah, 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 in the interval 1, 15 has a max. This is the problem. My answer is, it's continuous. This interval is closed and bounded. So from the extreme value theorem has a max.
Okay? Yeah. No. No, I don't think you guys know how to prove continuous since you haven't done what's it called? Limits. So you haven't done limits to start with, and you haven't done limits of real number of series. So yeah, I don't think you can prove that, even if you wanted to. For your sake, all the functions you're gonna deal in this course are gonna be continuous. Like, unless it's something really weird, and I mean it's defined on different intervals with different functions and whatnot. I've never seen that in the last 2 to 3 years. So yeah, you can assume that everything is continuous in this class. But yes, this is the solution to problem number 6. And the reason I wanted to let you think about it is just because I believe it's just like such like a showing of how strong and how useful this theorem can be and save you out of a situation. Imagine getting this problem, not thinking of the extreme value theorem, and starting to take a derivative of that ugly thing in the exam. That's going to waste at least 20 minutes until you realize there's no way you're going to solve that derivative. So, and I'll be already done in 1 minute and going next. So just whenever you're stuck and you ask for a maximum, just think of this theorem. Why not? Just maybe it's going to be helpful. I don't know. Anyway, let's do problem number 6, which is problem number 5 on the assignment. Gets confusing, I know. So the problem says something like, I'll share my screen immediately. Let me just copy it fast. Because we're going to go a little bit, I would say fast, but domain 0. Okay, extreme. Okay, cool. Actually, I think we have plenty of time. So this is my function, and I'm asked for the domain zeros, where is it positive, and the standard extreme, take a derivative kind of thing. Also, did I copy it correctly? Yeah. Okay. So when you're being asked for the domain, it's just asking you where is this function defined. That's the only question. Your assumption should always be that I start with the big interval. I start with minus infinity, infinity, and then I just cut out what is not working. So in this case, I look here. What do I see? I see a square root of x plus 6. What do you know about square roots? And that they have to be a square root of something positive. Okay. So my first observation is x plus 6 has to be greater or equal to 0. I just can't take square root of minus 20. It just doesn't exist. Okay. It exists, but not in complex numbers, not real. So not now. So I get that x has to be greater or equal to minus 6. Okay. If this is happening, I'm fine. This square root is fine. What other things can I get? 2 over square root of x. 2 over square root of x means that x cannot be 0 because I can't divide by 0. Are there any other restrictions? No. So to wrap it up, what is my domain? My domain is something like minus 6 to 0, and then 0 to infinity. You can write it like this. You can write it like
x greater equal to -6, x different from 0.
I don't really care how you write it. It doesn't matter. You can write it.
X is in -6 infinity minus the element of 0.
I don't really care. Okay. There are different writings. I know. I think I'm multinational in terms of mathematical notations, so I can understand all your notations. I just want to see the arguments clear for this and for this. Okay. I don't even really care if you give me the final answer. As long as I see the arguments that you thought of it, I'm fine. Okay. Let's look at
zeros and positive things. Zeros / positive.
the way I recommend doing this again is just by the table. I just find it pretty straightforward. So let's just do that. So my f of x.
So on case B, my f of x. So I'm starting from -6 and I'm going all the way to infinity. My f of x is here. I don't know how it looks. But then I have, I think it's 1 + 2 over x. And then I have square root of x plus 6.
Yeah. Okay. Cool.
And 0 here is not part of the thing.
Okay. Cool. So let's see what happens. If x is -6, this becomes 0. Otherwise, it's just positive, positive, absolutely everywhere.
This thing is negative here. Negative, negative, negative. At -2, it becomes 0. And then it just becomes, is it what it is? No, wait, sorry about that. No, it's my bad. It's positive, 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 positive. At -2, it becomes 0. Then how does this look? Let's see. If it goes -1, then it increases. So this goes negative, negative, and then it's positive, 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 positive.
Okay. So where are the zeros?
The zeros are at -6 and -2. 0 here, 0 here. And then positive, it's going to be -6, -2. And then, and without the sign, let's say 0, infinity.
Okay, everyone cool with what I did here? Agree? Awesome. Now the last part of this is double checking. Find the local extreme points, if any, which is a fancy term for take derivative, make it equal to 0.
So let's just do that. We have 2 minutes, easy take a derivative. We got this, maybe. I don't know. So I have 1 + 2 over x, square root of x plus 6. This is a product rule. So my f prime of x is the first one derivative, which is going to be -2 over x squared, square root of x plus 6. And then I have plus 1 + 2 over x, derivative of a half, 1 over the square root of x plus 6.
I think my computation should be decently correct. I might be wrong, but hopefully I didn't mess it up that bad. Okay, I know this is going to be equal to 0. So what do? I just multiply this whole thing by square root of x plus 6. So I get -2x squared times
plus 6 plus 1 plus 2 square root of x over a half or 1 equals 0.
Sure, seems about right.
Now I multiply everything with x squared. The whole idea is, so
Taking the derivative, did it a little bit fast because we're surely running out of time. But again, there's nothing fancy, so this I think you should be able to do. Made it equal to 0, and then how I solve this is I am just getting rid of these big denominators, they're called, of these denominators by just multiplying with them. I just want to get rid of them. I hate denominators. If you can work with them, work with them. I'm just not good at it. So the way I do it is I multiply with x squared, so I get minus 2 x plus 6 plus, and I have half an x squared plus 2x. There's no need for a parentheses, is equal to 0. So this is just equal to minus 2x minus 12 as far as I remember, plus 1x plus this with this cancels, so this is an x plus x is equal to 0. And yeah, this now I just group it everything up. I like multiplying by 2. Again, I absolutely hate fractions. So minus 2x minus 24 is equal to 0. I hope my computation is not absolutely terrible. So this is what I got. Now we just compute the ABC rule, and you get 2 squared minus 24 times 4, which is going to give you 100. So my x12 is going to be minus b, so minus 2 plus minus square root of 100 over 2. So my x12 is going to be, let's put it like this, x12 is going to be one side 2 plus 10 over 2, which is 6, and then 2 minus 10 over 2, which is minus 4. Yeah, I think this is correct. Okay. And I got the critical points. So maybe on the last part, I went a little bit faster, I guess. But the procedure is pretty simple. Take a derivative, make it equal to 0, and then solve for it. Okay. Have a great day, guys.